Alright, so I think this is recording. Let's go over some of our scale packet notes. Alright, so what do we have? Let's take a look at increasing, decreasing, and constant functions. First thing I notice is that although we have a definition to the right of that graph, that in this first graph, the definition that accompanies that graph is below it. Alright, so what do we see? We see here a graph that oscillates. It goes up and down. They have made part of the graph dashed line, and then they've made the part of the graph that we want to focus on a solid line. And they haven't given us the scale of the x-axis or the scale on the y-axis, but they have said that this point here has an x-coordinate that we're just going to call A. If you prefer to think of it as -1 for right now, that's fine. Over here, this endpoint at the end of this solid portion of the graph has an x-coordinate of B. And when we locate areas on a graph, we will use the x-coordinates to locate those parts of the graph, and we typically give that in what they call interval notation. And with interval notation, in this definition, they're actually not including the endpoints, because you see that if we made it a bracket, we would include the endpoints. Now, technically, you'll see textbooks use brackets or open parentheses in this definition. Later, in definitions of domain and range, it becomes very, very critical that you have the correct either bracket or parentheses. But right now it's forgiving, and it doesn't matter as much. What this interval notation means, when you have A comma B, you write the smaller number first, comma the larger number. You can rewrite this interval as an inequality. This inequality is a compound inequality. If you remember, the arrows always point to the smaller value. And if in a compound inequality, the arrows will always point in the same direction. So this is A is less than X, which is less than B. So that means that in this region that we have solid, if we pick some random point and we refer to that point as x comma y, what this is telling us, and what this interval notation is telling us, is that x is between A and B. It might be here, it could be you know, down here, or it could be up here. It's anywhere that's between A and B. Alright. Now, in the old days, when you took Algebra 1, you referred to the second number in an ordered pair as the y-coordinate. Okay? Now, instead of using y, we use function notation. So we've seen, I believe, that when you let's say that you had y equals 2x plus 1, and you were making a table to plot points to graph this, and maybe you put in just a few points. Well, if we plug in, if we let x be -1, -2 plus 1 is a -1. If x is 0, we have 0 plus 1. If x is 1, we have 2 plus 1. And we would have a line, and we can plot those 3 points, connect the dots, and we would see that we have a line. That was the Algebra 1 days. Now, instead of writing y, we use function notation and write a f of x. And this 2x plus 1. So when you see a table, they no longer use a y, they use this f of x. And when they substitute in a -1, they indicate that in notation by saying this function evaluated at -1 is equal to, and we have 2 times -1 plus 1, it's -1. So f evaluated at -1 is a y coordinate. So instead of writing y equals -1, instead of writing y equals -1, we write that f evaluated at -1 is -1. Now that notation also has the advantage that inside the parentheses is the x and outside what it's equal to is the y. So if we continue that, we've got f evaluated at 0 is equal to 1. That's what this point is, that all we're doing is substituting in 0 for x. And f evaluated at 1, well, 2 times 1 plus 1, that's 3. Alright, so why do I say all that? Well, to help you, you're at a point where you need to study definitions. You can't just, when they say your homework assignment tonight is to do problems 1 through 10, you have to spend some time first looking at definitions, then looking at examples before you jump in and try to do problems 1 through 10. Because if you jump in problem 1 through 10, the first thing that students say, well, can you do the first one for us? I don't know how to do it. Well, that's because you haven't taken enough time to look at definitions, to study the examples that led into doing those problems. You're at a level of math now where most of your time is going to be spent studying material rather than actually doing problems. So in this definition, we have a function is increasing on the interval from a to b. That's giving me a location of where to look on the graph to find my function. So if you're looking for when any point on the graph that has an x coordinate that is between a and b, that's what that interval notation is. A function is increasing on the interval from a to b if a is less than x, which is less than b, implies that f evaluated at a is less than f evaluated at b. F evaluated at a and f evaluated at b are y coordinates. So let's use the points the x coordinates a and b here. If x is a, then the y coordinate is f evaluated at a. And here, if this is b, then f evaluated at b is the y coordinate. So if you pick any 2 points, any x that's between a and b, and you compare the y coordinates, this is saying that as x increases to stay on the graph, y is also increasing. Alright, you can relate that. To make things simpler, think back in the days when you took Algebra 1 and you calculated the slope of a line. Given 2 points, you subtracted the y coordinates to get the rise, and you divided it by subtracting the x coordinates, the run, rise over run. If the rise over run between any 2 points in this open interval from a to b is a positive slope, the function is increasing. Like I say, as you move to the right, as x increases to stay on the graph, you have to go up, y increases. So it takes time and effort to understand mathematical definitions. And it's worth it. The better you understand it, the easier the later the problems will become. Alright. This next definition corresponds to the graph immediately below it. So again, we have a similar graph, if not the same graph. I didn't pay that much attention. It's going up and down, and we have located a point that we're saying the x-coordinate is A. We have a point on the graph where the x-coordinate is B. If we're interested in the part of the graph that has x-coordinates that are between A and B, they write that saying that you're on the open interval from A to B. Smaller number, comma the larger number. If you like to think of that in terms of an inequality, that means that the point, say, of interest, x, is the x-coordinate on this point. If it's between A and B, then it's on the part of the graph that we're interested in, that I have shaded here in green. If we pick any 2 points in this interval and we compare the x values and the y values, this time as x increases, as you move to the right, to stay on the graph, you're going down. So that's why we say a function is decreasing on the open interval from A to B. If A is less than x, which is less than b, implies that f of A is greater than f of B. Alright, here as x increases, y is decreasing. To relate it to something that you already know is to think of it in terms of the slope of a line passing through these 2 endpoints, A and B. You have your rise is negative, your run is positive. That's a negative slope. The function is decreasing. In the next definition, students find it the easiest to understand of the 3. Alright. And the picture really helps as well. Just as before, we have a part of the graph that we're interested in. We've made that part of the graph a solid line, and we're indicating that the endpoints of this on the x-coordinate is A and B. So if we look at any point on the graph where the x-coordinate is between A and B and observe what's happening to the y-coordinates, in this picture, the y-coordinates, the output of the function, is remaining constant. As you go from point to point, as you move, as x increases, you don't have to go up or down. The y is remaining constant. So a function is constant on the interval from A to B if A less than x less than b implies that the output of this function, f evaluated at A, is equal to f evaluated at B. So here at A, the y-coordinate is the same as the y-coordinate that corresponds when x is b. F evaluated at A is equal to f evaluated at B. For all points on this interval, on this open interval, we say that this function is constant. So let's see if we can understand these definitions a little bit better with some examples. In this first example, they give us a function that we're pretty familiar with. We've studied parabolas quite a bit. We know that it's a quadratic function. The newer software, when it comes to graphing things, will sometimes be capable of putting arrows on the end. If we have a graph that goes all the way to the edge of the graph, then we have to be able to assume that if we made the graph bigger, that those endpoints are just going on forever. So we go ahead and place those arrows there. Alright, so let's highlight where this function is increasing. We know that as you move from left to right, you're going down. So in this portion of the graph, we're going to see that it's decreasing. And then we hit the vertex of this parabola and things change. All of a sudden we start going up where the function is increasing. So if we think in terms of slope of lines, if you pick any 2 points in this region that I have shaded in yellow, if you pick, I don't know, a point here and some point up here, and you calculated the slope of the line that passes through those points, you're going to see its positive slope. That as you move to the right to stay on the graph, you have to be going up, so that's increasing. Alright, now let's shade where we're decreasing. Over here, as we move from right to left, we're going down. If you pick any 2 points, doesn't matter what 2 points, they could be close together. I'm making them far apart just so that we can emphasize that as you're going to the right, you're going down to stay on the graph, and down is negative. So if you were to calculate the slope of the line that passes through those 2 points, you would see that you have a negative slope. So remember that the x's determine where we're at on the graph, and the y's are the output of the function, and we're interested in whether those output, those y coordinates, are decreasing as you move to the right, or are they increasing as you move to the right. Now, to give our final answer, to describe it, let's come up for this part A. We need to describe what we've highlighted here in yellow. The point of interest is this vertex, which has an x-coordinate of 2 and a y-coordinate of -4. When we're writing our intervals, we're not interested in writing the y-coordinate. We're interested in writing the x-coordinate. So on the left, when I'm applying my definition of a comma b, I write a comma, that's the smaller number. So that's 2, comma, and now I come along here, and when I hit this arrow, that arrow is indicating that you're going to the right, but you're also going up. X is approaching positive infinity, y is also approaching positive infinity. But we know as you go from point to point, as x increases, y will also increase if the points of interest have x coordinates that are bigger than 2. So let's see if we wrote it as a sentence on the interval. On the interval from 2 to infinity, the function is increasing. Alright, so now let's take a look and describe B, where we've highlighted here in green. To describe this interval, on the left, the smaller values, this arrow is telling us that x is going towards negative infinity, y is going towards positive infinity. For the interval notation, we're only interested in the x-coordinates. So on the left this time, my smallest value is negative infinity. As you go from point to point, as you go to the right, as x increases, the y values are getting smaller. You're decreasing, you're going down. And that's true all the way until you hit the vertex. And the x-coordinate of the vertex is 2. So, on this interval, from negative infinity to positive 2, the function is decreasing. So on the interval, from negative infinity to positive 2, the function is decreasing. Now, part C is pretty easy. We don't have any portion of the graph that's flat, that levels out. You know, we have seen that when you're constant, there'll be a horizontal portion of the graph. There is none for this, so this function is never constant. So with one example, you're not going to be an expert, but hopefully that's helping get the point across, to understand the definitions a little bit better. Let's take a look at another example. This example is not from our library of functions. It's just pieced together with different segments and rays. If you have highlighters, you might find the highlighters helpful. If I use green for where the function is decreasing, as I move to the right, here I'm going down, so the function is decreasing. I hit this point and things change, because now I start, as I'm moving to the right, I'm going up, so the function is increasing. Then I hit this point and things change, and the output of the function, the y-coordinates, remain constant. All of these all these points on this portion of the graph have a y-coordinate of 3. Then I hit this point and the graph starts to go up again. Then I hit this corner, this point here, and it starts to go down again. And it continues going down forever. So in part A, we want to describe where the function is increasing. So let's do it like we did before. But instead of writing on the interval, which is singular, we have more than one interval on which it's increasing. So on the intervals, well, intervals, we use the x-coordinates. At this point, the x-coordinate is -5. At this point, the x-coordinate is -2. Guaranteed that if you're on a point that has an x-coordinate that's between -5 and -2, if you pick 2 points in that interval, as x increases, y increases. So on this part of the graph, we say we're increasing. Now, the same is true over here. The x-coordinate at this point is 4, which is smaller than the x-coordinate here, which is 7. Our interval notation always has a smaller number, comma, a larger number. If you're on any 2 points in this open interval from 4 to 7, as x increases, y increases. And on this portion of the graph, our function is increasing. The output of the function, the y values, get bigger. You're going up. When you have 2 separate intervals, we have to use a symbol that looks like a capital U, and it's called the union. The union of these 2 intervals. Now, we can think of union as the word or in your English. So if x is in this interval from -5 to -2, or if you have an x-coordinate that's on the interval from 4 to 7, the function is increasing. Alright, so in B, we need to describe these 2 portions of the graph that we've highlighted in green. In interval notation, we write the smaller number on the left. Well, here with this arrow, we need to break that up and think of that as the x is going to -infinity, y is going up to +infinity. So as I come in and move on the graph from tracing it out from left to right, I'm coming in, hitting an arrow, so we say from negative infinity all the way to the x-coordinate where it changes from decreasing to increasing. That happens when x is negative 5. Pick any 2 points where the x-coordinates are between negative infinity or less than negative 5 is basically what that said. Negative infinity is not a number, so I can't really talk about it as an endpoint in an inequality. It's just kind of an abstract concept. So any 2 points that have x-coordinates that are smaller than negative 5, as x increases to stay on the graph, y will be decreasing. So the slope through any points on this part of the graph will be negative. Or if we're in this other part of the graph that I've shaded in green, it has an x-coordinate of 7 all the way out to this arrow, which is positive infinity. So on this portion of the graph over these intervals, this interval or this interval, the function is decreasing. As x increases, to stay on the graph, you're moving down. Y is decreasing. Alright, and then this time, when it comes to being constant, if you're on the interval that we've highlighted in orange, the x-coordinate here is negative 2. So if x is between negative 2 and the x-coordinate here is 4, if x, pick any 2 points that are on this open interval from negative 2 to positive 4, and as x increases, the y values remain constant. So I hope that helps. Oh, we got a couple more. Try to do these a little bit faster then. I'll try to stick to the same colors. That as I'm going up, as it's increasing, I'll highlight it in yellow. Now here is kind of an argument, a fight starter. It looks like it becomes constant here, but it just is becoming really flat, and there's only one point in this interval here that has a y coordinate that's 3. So it's increasing very quickly, then its rate of increase slows down and it almost becomes constant, and then it starts increasing very quickly. Students have a difficult time sometimes with that idea. Here on this portion of the graph, it's decreasing. And here it's more obvious that it's constant than up here, because see how it's curving into that. Well, here it's a sharp turn, sharp corner. And I will not try to trick you on quizzes and tests with having a portion like this. I'll put dots here to indicate that it's a sharp corner, that there is a change. Alright, so in A, we want to describe what we've highlighted in yellow, where the function is increasing. So on the intervals, from negative infinity to the x-coordinate at that point, which is negative 6, from negative infinity to negative 6, or that's a union, this x-coordinate, negative 4, to this x-coordinate of positive 1, the function is increasing. Alright, now let's describe what we've highlighted in green here on the interval, well, we always start and move left to right. On the left, the x-coordinate here is 1, and on the right, I don't have an x-coordinate when I have an arrow. I just have this abstract concept of positive infinity, meaning it's going on forever, that it's extremely large. Alright, if you have any 2 points in this interval, as x increases, y will be decreasing. And finally, here where it's highlighted in orange, if we're on this interval, any 2 points in this interval, the x-coordinate is -6. At that point, and over here, the x-coordinate is -4. -6 is smaller than -4. The function is constant. Alright, so let's move on to the next one, which I think is our final example. Now again, we have a little bit of an optical illusion. If we could zoom in really close to the origin, we'd see that the only x-intercept is at the origin. That although it looks like that it's constant from -1 to +1 there, it's not. So that's a challenge for students to understand. Most of the time, well, at least some of the time, you'll have an equation that corresponds to the graph. You just won't mysteriously have a graph out of thin air. We use it for textbook purposes just to illustrate and understand the concepts. Most of the time you'll have an equation, and from that equation you'll be able to graph it, and you kind of work with both the equation and the graph to argue, well, that it's not constant. Alright, so to interpret this arrow down here on the left, it's going to the left, but it's also going down. So as it moves down, the x's are going to -infinity and the y's are going to -infinity. And over on this arrow, as you trace through the graph, as x is going to positive infinity, y is also going to positive infinity. Alright, so let's highlight where it's increasing at. Pick any 2 points that are on this portion of the graph, and as x increases, y is also increasing. And that happens all the way even through this point, because remember, that's the only x-intercept. So it's increasing very quickly, and it almost becomes constant, but it's still increasing slowly, and then all of a sudden it starts increasing very rapidly again. So we don't have any portion on this graph where it's decreasing, or any portion of this graph where it's constant. So in A, on the interval from -infinity to positive infinity, which on the interval of real numbers, the function is increasing. And we even call this an increasing function because it's increasing everywhere over its domain. This function is never decreasing, and this function is never constant. It is an increasing function everywhere. Alright. So that wraps up skill 2A. Sorry about it being so long.